Right, hi everybody, thanks for coming. So I'm very happy to introduce Rika Antonova to you, who's very kindly come today to give a seminar. So Rika did her PhD at KTH Stockholm, and then she's just finished a postdoc at Stanford, and now is setting up a new lab at Cambridge. So she's going to be based here in the UK, so thanks for coming to the UK and bringing all your expertise with you. First time I met Rika, I think, she was remotely operating a robot at Coral 2021, which I organised and set up, these teleoperation robots, and we had a conversation there. So thanks for coming in person this time. And over to you, and thank you for giving me a talk.
Thank you very much. All right. And this is going until 3, is that right? Just so I keep track of time? Cool.
The talk can be 40 minutes or so.
Yep.
Great, thanks.
Sounds good. All right. So today I will be talking about ingredients for efficient robot learning and exploration. I will show you some videos of the robots that I've worked with so far at Stanford, and I will also introduce my plans for what I'm about to set up at the University of Cambridge. So first of all, let's just talk a little bit about what I would think are the ingredients of efficient robot learning. So first of all, we need some basic understanding of what is happening in the environment. So we can do this with modern computer vision methods, like for example, using large vision language models to improve scene understanding. I'll talk a little bit about our recent work, TidyBot, on that. Then, of course, you need actual efficient, data-efficient learning. So I will talk about leveraging equivariance, differentiable simulation, and also various particular types of representations that speed up learning for robots. And then, actually, we shouldn't forget that an embodiment of a robot is not necessarily a given final point. We want to be able to modify that as well. And that, I think, can be done very well together in the loop with either optimizing the control as well, or also optimizing other parts of the robot, like for multimodal sensing, for example. All right, so let's start with what happens if your robot is in a room, let's say just a regular everyday environment, and it needs to understand where the various objects are. So in this day and age, we can set various large vision language model onto the task. They can parse the scene here, they can identify where the objects are, and the robot can even drive to these objects and with a camera kind of like get a better understanding of what the object is, and then understand what to do with that object. So in this particular work that was from last year, we have developed a system called TidyBot, where a robot can take in a few examples from a user of where the objects should go, and then it will also use the large language model to generalize these examples to special kind of like, as special cases of categories, it will generalize them to the category mapping from the category to the receptacle, let's say, where this category of objects should go. And so from just a few of the simple examples that the user can provide, it can understand then, okay, generally this is how I should tidy up the room based on the personalized preferences given by the user. So overall, the system works like this. We have overhead cameras that parse the scene, and then the robot drives up to the object and then takes an egocentric image of this object and queries a large vision language model about the object, understands its category, and then does the mapping to which receptacle should receive this category. Here we're using fairly basic kind of primitives for how to actually manipulate the objects, but as you can imagine, these can also be learned policies that are reacting to a specific object type later on. So just for kind of setting up this scenario and then showing that this generalizes to all different kinds of objects that have not been seen before, right? So most of these objects the robot has never seen before. It was just given one example of, let's say, one item of where it should go, and then it would generalize that, okay, this plastic fruit should go on the left, then the blocks should go in the middle, and then these kind of plastic tools should go on the right. So this is kind of a general setup. Of course, it also makes mistakes sometimes because, as you can see, it's identified kind of a banana more of as a toy block. But overall, the good thing is that now the user doesn't have to exhaustively specify what to do with these objects. It can instead, the user can instead provide just a few examples. And this works for other objects that are not rigid, like, for example, deformable objects, clothing that might be scattered on the floor or around the apartment. And so now, altogether, we have the system where, without too much additional work, we already have a general understanding of the robot about its surrounding environment when it's everyday environment, even if it's unstructured. All right, so now we would actually want to pay attention to the learning part, in the sense the learning to control the robot so that it does some more advanced tasks and advanced manipulation with the object. And one of the tools that I have been leveraging recently is equivariance. So overall, the idea is that we know that humans, given a few examples of solving the task, can very well extrapolate to understand how to execute task variations. So for example, this is a big Rubik's Cube at the University of Michigan. If you came across this cube like I did last winter, then you would instantly know what to do with it, even though obviously the person is not manipulating with the fingertips anymore, but is using their whole body to do this. But if you learn the policy for a robot, a dexterous policy, let's say the OpenAI policy that learned to rotate the cube, it is very unlikely that a robot arm would just drive up to this large cube and start doing something with it. So basically what we're missing here is that even after hours of getting some training data, or either to train from demonstrations, or maybe data that is kind of like obtained in a live manner by the robot, most of our policies would still fail when they face the real challenges. And that's because we sort of, as humans, expect them to do a certain level of generalization. Like, for example, if a robot can close a little suitcase, then a large suitcase shouldn't be a big deal, right? But as we know, if we've trained them only on small suitcases, then it's not going to know how to handle the large ones, or the ones with a slightly different shape, or the ones that it sees from a different perspective. So basically, to get to the level of generalization that we expect from humans, what we can do is we can use something that's called equivariance. And here we're going to be using that with the neural net equivariant architectures. And what this means is that basically, if your input object with which you want to manipulate is rotated, translated, and scaled, you would want somehow your policy to automatically react to that, automatically output the actions that are rotated, translated, and scaled appropriately. And some of this can be approximate, so it doesn't necessarily always need to be exact. But anyways, if you have the equivariance in the architectures, then you can, to some extent, accommodate this completely without retraining, so zero shot. So in this particular preliminary work that we have done, these are the kinds of demonstrations and kinds of objects that we've shown to the robot, as in like manipulation with this object by a human, so they're on the top. And then we expected the robot to be able to perform a similar task on these large objects. So the kind of examples that we've given were like the demo of folding a little handkerchief, a little cloth, cover a small box with a cloth, and close a small box. And we would then be able, by building in the equivariance into the policy learning architecture, zero-shot transfer to these large-scale scenes where the essence of the task is the same, but obviously the object has different appearance and vastly different scales. Here our inputs are point clouds, so that's why, for example, the colors here don't matter, so that adds a little bit more to the generalization. And so overall, this was our start, and this was just with the behavior cloning in terms of the policy learning part. Now, behavior cloning can get you some of the way there, but actually you would want a more powerful learning method, even if you're sticking for now with imitation learning. So currently the state of the art is probably the diffusion policy. And so in the follow-up work, we have built in equivariant architectures into the training pipeline for the diffusion policy training. And so here, ultimately, the idea is very similar, that you would have the actions that rotate, translate, and scale with the input, rotating, translating, and scaling. However, it's not kind of a trivial kind of copy-paste the architecture, because you actually need to ensure that at the end of it, you still have a valid diffusion process going on. So after all said and done, you again can get this zero-shot generalization. And here we have demonstrated it on a wider range of tasks. So again, you would have a human demonstration of the human performing a task. As you can see here, we're not doing very advanced kind of parsing of exactly what is happening with the human hand. We're just mostly using it as a sort of a parallel gripper-like action. But you could, these days, there are computer vision techniques that could take it to the next level as well. We process the data, treating this as a point cloud. We train now the diffusion policy, and then we deploy it on the real robot. And we expect this real robot to perform the same task with a different object in a different orientation of a different size and rescaled as well. So this is an example of luggage closing. You would observe that you can try to achieve something similar, for example, with some kind of augmentation. So of course, if you just deploy regular diffusion policy trained on this, on a luggage even rotated or on a luggage rescaled, you wouldn't really get any success rate. But if you somehow use some computer vision tricks in order to augment your data with some rotations, then potentially you could do a little bit better. So that's your 20% success rate. And then if you built in the equivariance, you can do even better, 60% success rate without any retraining. So if you wanted to get to kind of like to fine tune this, then you could get to 100% kind of for these kinds of tasks every time. This is an example of pushing a chair to the table. You can see here we have changed the shape of the table in the sense that now this table is more narrow. The ultimate motion could be very similar, but the policy is kind of trying to align, to create the alignment between the chair and the table. And of course, if you don't have the equivariance, then it will get confused with a table of a different shape now. Right? Even if you completely change the shape of the table, like for example, now the table is round, you could also get, in this particular case, a reasonably good performance. And here I will kind of come to the point where I would say that this is not purely due to equivariance, because here, of course, there is a highly nonlinear kind of change in the shape. But at the same time, because we have equivariance, we are freeing up some of the representational capacity for the policy to learn to kind of pay attention to other things. And this is kind of like one of the side effects that we have observed that is really beneficial. This also works with generalizing to slightly different objects, actually. So, for example, here we've shown the policy how to put in a t-shirt into the luggage. And here we're giving it an example of a hat. So obviously the object is very different, but it is kind of trying to mimic the motion that it has seen, and it doesn't get completely kind of confused by the different shape that it is seeing. Similarly with some other types of objects, like this is a different sort of deformable item. All right, and ultimately what we wanted to do is we also wanted to go to figure out how to do everyday tasks for kind of real scale items. So for example, when you make your bed, right, you're a larger human, you have more than one arms, more than one hand. How would you do it? Well, you could probably kind of like stand over the bed and cover it. Here we have two robots, so they potentially have a slightly different kind of capability, but still they can perform the task. And in this case, we can scale the task to arbitrarily large objects, which is a benefit here. Again, what they learned on was the demonstration from the top, and the only thing that you can see there is that this handkerchief or this little towel is kind of the type of task that the human is demonstrating is uncover or spread out this towel. And so this is the type of task that we kind of have in mind when we intend to cover the bed. And here, zero shot, we can accomplish this task even though the object itself is quite a bit of a rescaling. All right, so these are the kinds of tasks that we've considered. I also haven't mentioned some of the other ones, like, for example, closing the laundry door or trying to fold towels and so on. And we think that this framework is kind of sufficiently general now, that it can handle various types of objects. You can see here that we've worked a lot with deformables. We think that this is important because, in everyday life, you usually handle a lot of deformables, and traditional robotics has had kind of a lag in paying attention to them and really representing and handling the control for them. So it is nice to see that this here is kind of a capability that we get right away. So I actually just came back from Stanford, where were opening the Stanford Robotics Center, and we had to present all of these kind of demonstrations to a fairly large group of people. So at Stanford, all of the departments that had anything to do with the robotics, they kind of were brought together in order to contribute to the Stanford Robotics Center. And the grand challenge there was to accommodate more than 1,000 visitors over the course of a few weeks, where they would organize kind of the tours for people to see. And this would be both people who are, for example, from the local, let's say, Silicon Valley companies that are interested in investing in the space of robotics, people from very large corporations like Samsung, for example, was there, Toyota was there, and they're interested in kind of like more kind of corporate, large-scale exploration of what robotics can do, and also everyday visitors like, Stanford alumni or people even from the elderly care homes who are interested in, okay, how we can interact with everyday objects as well. So this was a lot of fun. I'll play just a few clips here.
After all, who can resist a robot that can pick up our laundry and put it in the hamper? Or bots working in tandem to make your bed.
If you watch this space, it is happening as we speak, literally. And the other good thing is that right now there's a lot of interest in it, so the hardware is also coming down in price, and the brains of the robots are becoming more smart. And we also had fun reporters who came in who actually asked to take part in the demonstrations. At first, of course, if you work in robotics, you know that usually you try to kind of like make a zone around your demos and not let anybody in so that they don't mess things up. But actually, they were quite friendly, so we felt comfortable enough. They asked us, is it okay while the robots are covering the bed to sit on the bed? And from the kind of technical perspective, there wasn't a problem because we segment kind of the part of the bed that is relevant to the task. So we wouldn't really try to do anything funny with the human there. But we haven't actually tried that before. So it was fun to see how it would happen in real time. And so then the CNET reporter actually had a fun idea about how to structure her kind of reporting piece around that. So I'll play that as well.
What you really need is a robot to clean up all of your mess. Say hello to TidyBot, a rolling robot with gripper arm that sees your mess, picks it up, and knows exactly where it needs to go. Into the bin, or a drawer, or on the shelf. TidyBot is just one of many projects that pave the way for general-purpose home robots. TidyBot uses a large language model to categorize your stuff. After you show it a few examples of where things belong, it learns where to put similar items.
And guess what? It can even make your bed. Make sure to subscribe and let me know what other robots you want to see going forward. Well, sweet dreams. Good night.
And so the most fun part is that we said, at the end, I'll play the piece from the other reporter in the meantime. At the end, we want to turn off the light. And we're like, okay, that's great, because we actually think that we can handle that because we're not working off of RGB images. We're actually, the point cloud-based policies are a bit more robust, and that did work. So anyways, this was a lot of fun. This reporter asked for the robot to hold the phone while he is recording his video. So we kind of quickly programmed the policy for him to do that. I think overall, this was kind of an eye-opening experience after being kind of in research for a while where we all really kind of aware of what the demo can and cannot do. Spending just a few months more on making this robust kind of takes it to the next level where you can really explore the things that you otherwise not try if somebody randomly, after your iCredit deadline came in and said, can I play with your demo? It does require a bit more work on everybody's part, including, obviously the students who put in way more hours than they would have otherwise put in just a video made for the paper. But I think overall also it makes the code more transferable and it makes kind of like the framework a bit more robust to what we can do with it next. All right, so this is for the data efficient learning, where you can leverage equivariance to improve imitation learning. You can do something similar. For example, I'm very interested in reinforcement learning, where we don't necessarily have demonstrations or want to improve significantly upon demonstrations. Likewise, you can build, this is a fairly general method, you can build in these architectures into whatever learning method you have, including RL. The other thing, though, that you can do is, of course, you can learn from simulation. And then you will have data efficiency in the real world because, well, you already learned quite a bit from the simulation. You now just need to close the sim-to-real gap. For that, one of the most efficient ways of getting a policy would be to have a differentiable simulator where you directly propagate the gradients with respect to where you want your target kind of object to appear. And so that is kind of, it has been an active area of research, and right now it's being kind of scaled up and sped up, and it's becoming actually useful. So you can do that. You can adapt the policy directly. You can also directly adapt the simulator. So, for example, if your object moves differently in simulation than in reality, if you have a way of somehow propagating the loss that would bring them closer together, then you can adjust the simulator itself. So the promise of the differentiable simulation is, of course, to view the simulation function f as a differentiable function, and then all that you need to do for optimization is to propagate the gradients. So with this, you can change the physics parameters, so get the real to sim, or as it used to be called, the system identification kind of the world in order to bring the simulator closer to reality. You can adapt the policy parameters, and you can also adapt geometry parameters. So you can change the morphology of your robot. Maybe you slightly change the shape of your hand or your gripper. Maybe you slightly change the shape of your arm to better serve the task. So I'll talk very briefly now about this real-to-sim problem of how to change the physics parameters directly. So this is the work that we've presented a few years ago at Coral in 2022, where you can have a differentiable simulator. You can see that on top. And within a few episodes, you can basically adapt the properties of this deformable in such a way that it resembles how the real deformable moves. You can also adapt the policy parameters. So here, this is just in sim for now. You can change the policy of the slattle that picks up the 2 sugar cubes. And we've also shown that this transfers to reality. So I have videos where we scoop 2 of these sugar cubes in real as well. Now, this all sounds nice and fine. But actually, if you try to plot the loss landscapes that you get from these kinds of simulations, they don't look like something that a single gradient descent could handle, right? You can see a lot of the local minima there and pretty non-trivial landscape. And moreover, when you look at how these gradients actually show up, you don't even have kind of valid or stable gradients across the whole landscape. So this landscape is just like a 2-dimensional slide, obviously, for higher dimensional landscape, because we're optimizing here more than 2 parameters. So the point of this work, which we called Rethinking Optimization with Differentiable Simulation, was to really investigate what are the challenges there, what else do we need in addition to the differentiability in order for this to scale. So other types of things that you can have is, for example, even on very smooth landscapes where you would expect the gradients to do really well, you can have these plateaus. So if you try to take a gradient on that plateau, right, it would take forever for it to actually go down to some meaningful minimum. And of course, you can also have issues where if you have rigid context, then you would have landscapes that look somewhat like this, very, very spiky, very discontinuous if you have explicitly kind of modeled the different kinds of contexts happening at different time. And this is actually a simplification of what happens in the reality with the simplest tasks, like, picking up like regular objects, right, and reorienting them in hand or doing basically any kind of contact-rich manipulation. So with that, what we were arguing for in this particular work is that we need some kind of a new method that combines the differentiability and ability to descend rapidly on the nice and smooth parts of the landscape with something else that can look at the landscape globally and that can also overcome kind of the local bumps, even if they're very very challenging. So for that, we've created this method that we call BO-Leave. So it combines a global search via Bayesian optimization. So this is something that kind of models the predicted kind of performance or predicted alignment across the whole kind of range of parameters, so globally. So we've combined that with a semi-local optimization. So these are more like evolutionary methods that kind of look at semi-locally where, in which direction should I be going in order to improve something, not only looking at the gradient, but kind of looking a little bit more broader, but on a kind of semi-local scale. And then once you arrive at a reasonably interesting location, and if you see that it is pretty smooth, then you can take a dive or a leap where you use the gradients in order to make very rapid progress on the nice parts of the landscape. So this is one of the kind of backbone, let's say, methods that I will kind of keep working with, because you can plug in different improvements for either the global part here or the semi-local or the gradient-based part. And as you improve all these different components, of course, the whole optimization will get better as well. Now, how do you connect it to the real world? The way that you connect, let's say, mesh-based simulation with something where you have, let's say, a point cloud in real that you actually, your robot or your real camera takes, is by using, for example, the differentiable point cloud sampling here, where in the previous work that we've done, we have made it possible to propagate the gradients back from the loss that is a chamfer distance loss. So chamfer distance, what it does is that it looks at 2 point clouds. In this case, one simulated and the other one is real. And it says, okay, I want the overall alignment between these 2 point clouds to be kind of maximized, right? And then this is just a standard loss that is used in computer vision to align when you need to align 2 point clouds. Here, the distinction is that one is simulated, one is real. And this way, you can actually, if you introduce a differentiable point cloud sampling in the middle there, you can propagate that loss all the way back to this differentiable simulator, all the way to, let's say, change the properties of the physical properties of the simulator. And the good part here is that you can then do the learning part a lot quicker, so you don't need to collect a lot of data a priori, build up some sort of big model. You already have the differentiable simulator based on which you can start, even if it's pretty far from the output that you have in reality, as long as it generally kind of represents similar objects, like you have a deformable shape here and deformable shape in reality, then you can get the that your time to align with the real world would be minimized in this case. All right, and this is just some examples of how you can very quickly distinguish between a deformable that folds very easily, or like a paper towel deformable that, paper towel deformable that does not fold, so has a bit more stiffness and is still deformable, but of course maintains its shape much more than the cloth that is highly deformable. All right, now you don't always have a differentiable simulator. So in this particular case, when I'm talking about the differentiable simulator here is an actual program with some physics coded inside of it in such a way that the gradients can be propagated through. So somebody actually needs to set it up. It's a non-trivial piece of work. You probably have worked with simulators that are non-differentiable, so you can't natively propagate the gradients through, but you can still do things like real to sim alignment if you have some inference methods that can cope with it. So, for example, here, this was our other recent work that looked at this from the distributional perspective. So it basically says we will have a kind of a distribution over the physics parameters of, in this case, our deformable object. And we will kind of wiggle this object on some, arbitrary trajectory just to see how it deforms. And we will sample from kind of a range of these parameters, so from this prior distribution, and we'll have a range of behaviors. And then we will encode the motion of this object. You can use off-the-shelf methods here that are doing key point extraction. So there are a few works that can let you do this fairly easily. And so these key points then would represent kind of a lower dimensional, let's say, version of how overall your shape of the object changes. Now, with this, you can reasonably well kind of understand what is the shape of the object and track them. But if you try to learn some sort of a policy based on that, then you might have trouble, because these key points, they will jump around on the object. They will disappear in one spot and appear in another spot as you change kind of the visibility of different object parts. So here, the point from us was to improve this representation by embedding this key point-based representation into a larger space. If you're coming from the machine learning background, then you know this kind of like general trick where you can sort of map it into an infinite dimensional space where it sounds like you've made it more complicated, but actually you kind of like have more representational capacity there. And if you do it in an efficient way, then you can get some nice properties. So for example, here we were looking for permutation invariance, for robustness to noise, for good distance metrics so that we can actually compare the states of the two objects, and for the continuity of this sort of mapping. And so you, if you set these as targets, then there are kind of representations that you can use in order to get all of this and compute the representation efficiently as well. And so in this particular case, we've used Fourier features, and we've developed an adaptive version of random Fourier features. So the way that this works is that you start with these key points, and then you, there is this work from 2013 from Arthur Gretton's group, which is actually PCL, which is called the kernel mean embeddings. So you can, or just kernel embeddings of distributions. So a kernel mean embedding in particular would kind of try to model your sample, just a sample of your key points, as sort of representing the probability distribution that governs the whole shape of your object. So as your object moves, right, or as you take different samples of these key points, this kind of lets you see overall what is the distribution, meaning what is the shape of your object. And this is sort of a theoretical object, but if you look at it from a practical perspective, you can create kind of an approximation that is based on these sample key points, and that approximation can have nice properties, like it would basically be just a vector of floating point numbers with a well-defined distance metric that you can then compare, and with this you would get a representation that has the nice properties that we were looking for, like the permutation invariance and robustness to noise, and a good distance metric. So you can think of it as basically taking the representation that we had, just the key points on object, mapping this representation from this fixed dimensional space into this infinite dimensional space of functions. So in this particular case, we are mapping this on sine cosine functions with certain frequencies, and then projecting, so because ultimately our kind of mapping here, we would also have a finite dimensional vector here that we map to. You can think of it as projecting from this infinite dimensional space of functions onto a subspace. And there are various kind of theoretical works that kind of show or look into what are the properties of this projection. And in practice, and these properties are, what we wanted. And in practice, we have verified that actually they give us good practical performance as well. So with that representation, what you can do is you can build this representation directly into a neural network layer. So this is not some kind of extraneous thing that you'd have to do. It will be just directly mapped into this and also differentiable. So you can adapt this representation as you go. And this lets you basically more easily work with the inference methods that would, for example, help you to infer what are the parameters of what are the physics parameters of your objects, given that you have a certain real kind of example of a real trajectory. So with this all together, you can iterate on this. You can take, one real trajectory. You can compute this kind of like better alignment. You can then shrink the original probability distributions that guide the physics parameters of your objects. And you can again go through this and shrink them more and ultimately come up with a version of the simulation where the deformable objects, they're still highly flexible, right? But they behave more like the real objects and not like the just some default simulation. So the things that we worked with are this winding task. And here, just to show you kind of what sort of effect this has, is that the kind of experiments that used our representation here were able to reduce the distance to ground truth much, much quicker than the standard inference methods that did not use these representations. All right, so at the end I was saying that we also shouldn't forget that the hardware is not necessarily final. We can adapt that as well. And so this is something that can be done within the framework of differentiable simulation 2, where you can propagate the gradients through to changing the geometry parameters. So here, there was some previous work that is called DiffHand coming out of MIT, where they looked into using cage-based deformation, which is a very well-established technique in computer graphics, in order to represent a few points on the object that could be stretched, such that the overall morphology of the object or shape of the object changes. So this way, you don't have to worry about kind of every single sort of vertex on your highly dense mesh, but you can find a nice kind of representation for this manually. You can construct a representation for this manually, or you can use the cage-based deformation algorithms in order to compute these things automatically. But when we looked at this prior work, basically what we found is that the loss landscapes that this resulted in were rather simple, rather smooth, because this previous group, they worked with things like reaching a certain target, right? So changing the length of the robot's arm in order to reach a particular target. So this is a very, very kind of smooth landscape that results from this kind of task. We were interested in much more contact-rich things, like, for example, if you wrap a rope around a certain tool, what would happen? And obviously, there are a lot of contacts that this rope makes, especially if you're just learning how to do it and not kind of just showing the final result. So the loss landscapes look a lot more spiky, and if you remember from that previous work, right, we have identified that when you have contact-rich interactions, you would have these very challenging landscapes. And so in this particular case, we thought, okay, now we need to develop something that will kind of learn a result that is robust to different changes that happen when you change kind of the way that the object interacts with the tool in this particular case. So the idea here was to learn sequentially, so kind of benefiting from the work on continual learning, where you would learn from kind of one batch of data, and then you would start learning on the second batch of data, but you need an additional loss that would ensure that you don't forget the knowledge that you've learned from the first batch of data. And so this way you can make these batches a little bit more tractable for learning, but at the same time be able to kind of make a policy or make your changes in such a way that it is kind of represents the motion regardless of what is the orientation or what is the kind of lower level interaction that your object has with the tool. And the other thing that we had is that, okay, you can also kind of decompose this problem a bit more, where you can change, optimize subsets of your, let's say, parameters each time that you do this, because now you have this kind of lifelong learning setup. You have multiple opportunities to learn. And so in this particular work, we were adapting the shape of tools. So sometimes people adapt the shape of gripper. It's kind of a similar idea. So here the gripper is a standard robotic gripper. It grabs a tool, right? And it tries to execute a certain task. For example, the task here is to wind the rope around the tool. But the shape of the tool now can be changed, and the reward for this whole thing, or the loss, depending on how you look at it, is to make sure that the rope stays on the tool. So you can then change the shape of the tool automatically by propagating the gradients through to change the morphology or to change the shape of the tool. Right, so other tasks that we've explored is, for example, pushing a round object. It is slightly uneven surface so that it is hard to kind of predict how it would roll. And so this is kind of an automatically generated shape of the tool that would kind of hug this object, starting from a kind of a flatter tool. And similarly, winding the rope around the tool, as I was saying before, this is the kind of output of the optimization. From the human perspective, you would say, yeah, well, of course, you have to have the sides that sort of catch onto the rope. But mind that this was done without any sort of prior knowledge of what has to happen here. It just has an objective that, the tip of the rope shouldn't fall too far, that's all. All right, so in this way, you can change the morphology or the shape. You can also change other properties you can imagine, like material properties, for example, and you can adapt the robot itself instead of adapting the tool. These are the things that I would like to look at as well. But you might also be interested in kind of what sort of things you're using for sensing, because one thing is kind of how you manipulate objects, but also it's very important to get enough information about the objects that you're interacting with. So one of the things that was also part of this Stanford Robotics Center opening demos was an experiment with a novel sensor. So this is a tactile sensing array from Mark Rutkowski's group, from basically one of the students who was developing this as part of his thesis. It uses a magnet and a sensor in order to figure out kind of like how to estimate the forces, including the shear force, which is actually uncommon for low-cost sensors. And it pretty much costs, I mean, if you set it up in a large-scale production, it would be like $1 or less. But right now, maybe you would spend 10 or 20 to put together this prototype. So it's pretty low cost, given that getting these sensors right now in the commercial way would be pretty costly or impossible in the case of the shear force modeling. So the way that it works is like this. You can basically put these taxels on a somewhat flexible film. So you can actually wrap around this film around the arm if you wanted to, so it can conform to different areas of the robot. And you can activate multiples of them at the same time. And if you have kind of multiple interactions between this, then you can kind of understand then what happens to the object, what forces the object is exerting on the arm in this case, for example. So as a part of the opening demos, we've shown how to carry the tray or how to carry the Tupperware container here with some food. And as the robot rolls, it is balancing this food. And also it has a way of understanding when the user places the food on to the arm and when the user takes it away. All right, so with that, you can adapt your hardware to have a better shape for your task. You can adapt your sensing to have a better kind of understanding and awareness of what is happening with your current environment. And I want to focus on this aspect in the future here at Cambridge. And I also want to explore things that have to do more with the side of the policy learning, that is in reinforcement learning, and kind of combining the optimization that I've talked about before that looks at things globally together with the more local methods that are RL methods. So one of the things that I will be looking at, and again, if people have interest in this area, I would love to talk about this, is co-evolution of hardware and policy learning. So frequently we just think about either manual design of hardware or kind of maybe somewhat automatically kind of guiding what should happen with the hardware, and then we learn a policy on the on the final result. But what I want to do is I want to actually do this all jointly. It's a humongous space, so you would need to do some very intricate kind of like global optimization here that has to be efficient enough in order to handle this whole thing, but ultimately I think that it's possible. With that, the learning of the policies I actually want to do with RL as opposed to imitation learning, because here there would be the need for novel methods because they can be, the designs that we arrive at might not resemble anything, related to humans at all, right? So then a human wouldn't be able to teleoperate or to somehow demonstrate how to solve the task with this novel hardware. So I want to kind of push forward the state of the art in RL itself in order to be able to come up with advanced policies. And finally, in the context of robotics, what I want to do is I want to put all of this onto kind of the groups of robots that are able to collaborate when they have the embodiments that are not necessarily the same. So again, you might imagine that you would optimize this and come up with different shapes or different embodiments for different tasks. And then you would have these robots, but if they're solving a whole new task, given their current embodiment, then it would be very interesting for them to understand kind of how to collaborate and how to leverage their respective strengths. All right, so in terms of thinking about this co-evolution of policy learning and hardware, the things that we would be looking at is, for example, changing morphology, as I have described, also changing the way that the hand, in this case, is actuated, the material properties of the hand, potentially if this is extended to the arm, then also how you're covering arm with the sensing and the material properties of that. The sensor placement for the hand, it is most likely to go on the fingertips, but if you're doing, for example, tasks where you're engaging the back of your hand, that also you also might find that the sensor placement is something that could be better derived kind of automatically in a task-oriented manner. And then the challenging algorithmic part here would be to parameterize the space of the reinforcement learning and control, let's say model predictive control methods, in such a way that you can efficiently search through the space. Because right now we have a whole zoo of different approaches that you can try, and if you went and one by one tried all of them with all the different hyperparameters that they have, that would take forever, right? So what you would want to do is you want to somehow find relationships between them, systematize them, and when you're picking which method to use, using the information that you have at the end of your trial in order to understand how the nearby or the similar methods are related to this method. So this will be kind of a challenging large-scale project, and I'm looking for new people to join my team in order to take part in that project. For the case of the reinforcement learning, what I'm interested in is basically I've talked with you about these distribution embeddings earlier, right? We were using them for an advanced representation for our deformables, but ultimately it's a very general technique that basically says I can look at a stochastic object, I can embed the stochastic object, and this embedding has some nice properties. So in this particular case, the stochastic object is a reinforcement learning policy. It's a big beast, right? Because it basically has to know what to do for every state that is probabilistically somehow sampled. And you have transitions between states, so it's like a sequential thing as well. So it's a pretty large item. But ultimately, I have ideas also how to kind of like view this whole item as a probability distribution itself, embed it, and then once you have this embedding, I mentioned that you get sort of for free a well-defined distance metric. And once you have a well-defined distance metric, you can maximize this distance metric if you want in order to get policies that are somehow different from each other. And with this, what you can do is you can effectively get unstuck from your local minimum that your reinforcement learning kind of would drive into usually when we deploy it, for example, on contact-rich tasks. So if you try to solve a task in a particular way and you sort of increase your reward and you sort of get there, but you don't really solve the task, currently, it is very difficult to say, try something different from this, right? So this would be a way to say this, and I will connect this to the work that we've done before on learning independent relations. So these would be kind of like independent policies, independent in the sense that they're in a sense that they're different from each other, and in a sense that sort of maybe combined all together, they span the space of effective policies for kind of a given embodiment and a given task. All right, and lastly, as I mentioned, so I'm getting a lot of the kind of hardware and working with the hardware, like, robot arms, robot hands, mobile platforms. There are also Amanda Prorok, whose team works with various vehicles, of quadcopters, and also multi-agent learning. So I think altogether it would be a very nice collaboration kind of in our department at Cambridge. All right. When I was giving this talk in Europe, in Germany, I just went to Corel in Germany, and after that gave a few talks. They said, oh, okay, yeah, Cambridge, that's good, but maybe you can show a picture because maybe people kind of like don't know how it looks like. And I thought, okay, well, that's a good idea. You probably know how it looks like. And then I found this video from University of Cambridge, which like shows very nicely how I view it. It's beautiful. It's sometimes sunny. And kind of people in Europe, like they don't think that this is possible, but actually, you know, I see it now that I'm there, so this is good. It's a different vibe, I would say, than what you have here in London. Obviously, you're in the middle of a big city, that is a small town. But I think it kind of creates a nice environment where you can have kind of a small, let's say, smaller group collaborations, and at the same time, you're very much connected to, you know, everybody else who is in London and so on. All right, so that's the setting currently, and my lab is going to be called the Resilient Autonomous Learning Lab. Now we can go to questions and still hopefully have some time, and I'll play the video from the Stanford Robotics Center opening with the part where people came in to see our work.
Thanks so much, Rika. Yeah, really nice to see you covering like everything in robotics, basically, all the way from the hardware to the sensors, the control.
No underground robots yet.
Nothing underground yet.
Nothing in space. Oh, I forgot. We had something in space, but
right.
I'm not actively working on it yet. Yeah.
Okay, we've got time for a few questions. So if you have a question, please put your hand up.
Yes.
Ivan?
Yes. Great. Does it mean there are some tasks in your experience that are harder to learn or not possible to learn? It doesn't really constrain it in terms of learning. So it's not like you're saying you restrict it to something. There is a way to deploy equivariance in such a way, but okay, we obviously didn't do it. What you do pay, of course, is the network structures take a little bit more time to train. So it's not an order of magnitude more, so it's not like it's a huge difference, but yes, you do have that. Potentially, maybe you could have issues where something is harder to learn because it's a more advanced representation. We haven't run into that yet, but you've seen the tasks that we had are not the most advanced tasks ever, right? So it might be the case, you know, that it remains to be seen. Yeah.
Thank you very much. One thing that you didn't develop, but you just mentioned right at the start, were the large language models that you're trying to think with. Could you say anything more about how you're expressing your tasks and making that link?
Right. So hopefully it doesn't let me jump to that part, because it's always easier to just look at. I think we'll get there. Yes. Right. So here it can be either a prompt and the user types in something about black shirt goes into black box or goes on the couch. Luckily, this sort of interaction right now is just natively handled by LLM, right? So you can write in free-form text, like what do you want to do? That's not a problem. We've also had initial experiments with showing images to the LLM, to a vision language model. So it is able to interpret something like this, like an arrow goes here, and therefore you have sort of this relationship. What we don't do with this, where it's still lacking, is on the low-level control. So as you imagine, this is a high-level planning that understands something about everyday objects, understands something about relationships, receptacles, drawers, couches, and so on. Well, if you try to, for example, explain how something should be opened, untied, or tied, or uncovered, that is a little bit more challenging. So actually, Ed has done a little bit of kind of exploration early on with this, and maybe they're doing more of like getting that knowledge of how to move specifically from the large vision language model. It is potentially technically possible, but here we're operating on a higher level where it is task planning level as opposed to policy kind of learning level, and the policy learning is left to the other works that I've presented. What?
So you have to plenty of open work.
For the lower level, yes. And this is actually one of the interesting parts from the research perspective. Maybe not from the application perspective, because there are other ways of doing it, but from the research perspective, it's like, is there physical knowledge enough that this thing has agglomerated inside that it can output in order to inform how the robot should move? And it is not entirely clear how much of this physical knowledge is there. So, for example, it has been shown that these large vision language models, they have a bit of difficulty understanding sort of spatial reasoning. So if you just ask it what object it is, it's perfectly fine. It's going to do, sometimes superhuman performance, right? But if you try to sort of reason about how to, let's say, spatially, how the objects are spatially positioned, actually humans are still a bit better in that. So potentially this knowledge should be embedded in it in some way, because it sees people talking about it, so it can parse it from language. It sees how objects change from vision and from videos that it's learning from, but it's still tricky to kind of get that knowledge out. But yeah, that could be a future exploration.
Thank you very much. From your experience, how much complexity does adding a model takes to the robot add? And adding it to your system, what does it allow you to tackle? Like scientific?
Okay, scientific. I see. Very good question. Let me go play the one where it moves. So what does it add from the scientific perspective? So from the scientific, obviously it adds a lot from non-scientific perspective, where you can just handle the tasks that you otherwise wouldn't be able to handle. So from the practical perspective, it relieves you from the need to just like always make a lab setup. That's obvious, right? From the scientific perspective, what I like is that it lets you change dynamically the scope of your task. So you're not always saying, okay, here are my objects and here is my workspace. Your workspace actually adaptively shrinks and adjusts like this. This is not something that we have explicitly kind of looked at before with the robotics that handled kind of stationary arms. So I think there is kind of, this obviously connects it to navigation, this connects it to, things like that, like SLAM and so on. But the interesting part there from the manipulation perspective is like, where should your attention be? Not necessarily the neural network attention, but also neural network attention, and how should it shift based on what is physically happening with the object.